Okay, we're going to have a short lesson on parallel circuits. Again, I'm sorry not to be able to do this with you in class because it's really fun to talk about and act out, and so you'll just have to imagine, play pretend a little bit. Okay, so the idea is that unlike series circuits, where everything was in just one big circle and all the charges had to go through every resistor, this is a drawing of a parallel circuit, and you're going to see that every charge leaves the battery, so this is the positive end, goes through, so this is your total current right here, and then the charges have a choice, right? They can go through resistor 1 or resistor 2 or resistor 3. And our goal right now, just like it was with series circuits, is to change this complicated circuit into a simple one that just has a battery and a resistor. And this is really REQ. I just got the picture from somewhere else. But this is REQ, this is V total, this is I total. Okay, so hopefully that makes sense. And you'll notice current 1 goes through resistor 1, current 2 goes through resistor 2, current 3 goes through resistor 3. But because there's a choice, that means that these three currents may very well be different. And in fact, what happens is that those three add up to be this. So, you remember the silly shopping analogy from the last movie? For this one, let's pretend that once again you get on off the bus with me and I give you each $100. That's basically your voltage. But the thing is, you have to spend it all at one store and you get to choose, right? So if you want to spend $100 at Starbucks, I suppose you could do that, or $100 at Nordstrom, or $100 at Old Navy, or something like that. And then you come out of the store and you go back to the bus, you get $100 more. Again, very much a pretend story. And you go, if you want, to a different store, right? We can't track every electron and see where it goes. We just know that some electrons go through each one. Now, the deal is that based on the resistance, that's going to dictate how many electrons go through the resistor. For example, imagine that we're all in the CA, okay? And there's a performance going on in the CA, and suddenly a terrible fire breaks out on the stage. So there are a whole bunch of ways to get out of the building, but and the easiest one might be, let's pretend you're a junior and let's pretend that you sit really towards the back, and so the easiest one to go out is right behind you. But that's where all the freshmen are going too, and so, is that really the best one, or should you go sort of to the side, right? The point is, if everybody's going for the same exit, it's not necessarily the best exit to go out. That's sort of how the electrons feel. This might be a really easy resistor to go through because it's a small resistance, but if they all went through it, then that would just make no sense. So they divvy themselves up, and there is an equation that dictates how they divvy themselves up. Okay, so let's keep going. Again, here's our picture. And like I said, I1 equals the current that goes through R1, etc. for number 2, etc. for number 3. And again, we talk about the voltage drop across R1, R2, and R3. And no surprise, Ohm's law shows up, and this is how those are related. And there's a typo there. I should have said I1, I2, and I3. Sorry about that. So in your notes, which I sure hope you're writing, make sure this says V1 equals I1 R1, V2 equals I2 R2, V3 equals I3 R3, because those are different currents, unlike with series. Now, in this case, V total equals V1 equals V2 equals V3. So we're going to put voltmeters across each of these, but if this is a 9-volt battery, then there's 9 volts across the R1, across the R2, across the R3. But as we said, the I totals is the sum of the currents because all of the electrons must choose, and in total, they are going to divvy up. And once again, V total equals I total REQ. All right, if you need to pause the video to write these notes, by all means, I think that's a great idea. Okay, so for a parallel circuit, this is really different. This is a much more complicated equation for the REQ. And what you do is you take the reciprocal of all of the resistances, add those together, and that gives you the reciprocal of the REQ. We'll do some practice with this. And just like for series circuits, all the power equations are the same, right? P total equals this. And if you did, oh my gosh, there's another typo. This should be I total V total. This is a stupid equation. That's terrible. Okay. Let's Let's see if I did it right here. Yeah, I did it right here. So since P equals IV, this should be P total equals I total V total. Sorry I didn't catch that, but I'm not going to make this video over again. All right, we'll just check in class to make sure everybody has the right equations. Okay, so what I did is I set up a circuit, and you can see 3 different resistors, 20, 15, 10, and really, if you've got power and nothing else to do during the snow day, I think this is a pretty cool exercise to play around with this. So the deal is 9-volt battery, and all the current comes out, and it's a total of 1.95 amps. And you'll see that not equal amounts of currents go through the resistors. In fact, the biggest resistor, the 20, has the smallest amount of current. And then the smallest one that says 10 ohms, I don't know if you can see it, has the most current. And if you were to add up these 3 numbers, guess what you would get? That's right. 1.95 amps. Okay? And in the next 3 slides, I'm going to show you the difference is that I'm going to move these voltmeter probes, that's what they're called. I'm going to move them from resistor to resistor. So on the bottom resistor, it's 8.995 volts. Wow, that's awfully close to 9 volts. And as I go to the next one, look, same. Look, same. Isn't that exciting? So V total equals V1 equals V2 equals V3. All right. So now it's a chance to try the problems. Do 79A through G and 80A through F, and pause, and when you come back, you'll see the answers. See, there are the answers. Okay, I'm going to talk you through. I know it's going to be crazy fast. Sorry. Okay, so starting with 79, I'm going to do A through G. So for 79, you've got a resistor A and a resistor B, and they're 10 ohms and 5 amps. They're connected in parallel, and it's a 12-volt battery. The equivalent resistance, so 1 over Req equals 1 over 10 plus 1 over 5, and you should get Req equals 3.33 ohms. For the current total, I total equals V total over Req. That's 12 divided by 3.333, and that's going to give you 3.6 amps. And the voltage across each resistor, since it's the same, V1, V2, and V total are all 12 volts. For part D, the current running through, so I took I equals V over R, 12 over 10 gives you 1.2. For E, I did V over R equals 12 over 5 equals 2.4 amps. For F, I did P total equals V total squared over Req, and I got 43.2 watts. And just individually, for the 10 ohm resistor, I did V squared over R, so 12 squared over 10 gives you 14.4 watts. All right, it'd be kind of interesting because you did a similar problem when they were in series. You did, ideally, number 76, and it might be interesting for you to compare the power. Go back and look, and you'll see that the total circuit for series generated a lot less power. Okay, for 80, hopefully you've done this one too. This is really similar to what you did before, but now these are in parallel. So the equivalent resistance is 1 over Req is 1 over 48 plus 1 over 68 plus 1 over 10, and you find the Req is 7.38. And notice that the Req is smaller than any of the individual resistors, right? That's going back here. We were dealing with a 10 and a 5 ohm resistor, and 3.33 is smaller. Here we were dealing with a 48, 68, and 10, and 7.38 is smaller. That will always be true. Okay, for part B, find the total current. I total equals V total over Req, 12 over 7.38, and you get 1.63 amps. For part C, sorry, I'm doing this on Friday night and I'm sleepy. V total equals V1 equals V2, etc. It's going to be 12 volts for each of them. For part D, I just did I equals V over R. See, I told you Ohm's law was going to be your new friend. So I equals V over R, and that's going to be 0.25 amps for the 48, 0.18 amps V over R for the 68, and 1.2 amps for the 10 ohm. For E, it's P total. P total equals V total squared over Req, and you should get 19.5 watts. And then for the last one, P equals V squared over the individual resistor, so 12 squared over 10 gives you 14.4 watts. Again, this is using a lot more power, or actually, sorry, producing a lot more power than it did in series. And I'm going to hopefully get a chance to show you a pretty cool demo about that. So that's it. Hope you learned lots. Go do your homework. Have a good time. See you in class, I hope, really soon.